Hello and welcome to this lecture. So, we have been talking about how a matrix with respect to an operator with respect to some basis, if you compute the matrix, it becomes diagonal, this basis, that basis, it's all a little bit confusing. So, I am going to go into detail here and talk about these coordinates with respect to different bases, matrix with respect to different bases and clarify all of that. Okay. Let us look at this in close detail. First, we will start with coordinates of a vector with respect to different bases. So, usually we consider canonical basis, right. So, our ground truth, our basic assumption is canonical basis. So, let us say a vector v is x1 to xn in canonical basis. So, what does that mean? V can be written as x1 times e1 plus so on till xn times en, right. So, this is what it means. Now, let us say we have another basis u1, u2 to un, and each of these basis vectors is given by n coordinates with respect to canonical basis. So, what is u1? u1 is u11 to un1 in the canonical basis. Un is u1n to unn in the canonical basis. Okay, so this is just each vector is given, each basis vector is provided once again in the canonical basis. So, what does that mean? u1 is u11 e1 plus so on till un1 e1 en. Un that way is u1n en. No, sorry. Okay, so clearly un is also u1n dot 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 u1n, which means un is u1n u1 plus so on till unn en. Okay, so hopefully you see this. So this is a new basis. Now I want to ask, what are the coordinates of v in this new basis? I know v is x1 to xn in the canonical basis. What are the coordinates of v in the new basis? Okay, so we know this, we have seen this before. Suppose v is x1 prime to xn prime in this new basis. What does that mean? V, the same vector v here, becomes now written as a linear combination of u1 to un, and those coefficients are x1 prime to xn prime, right. So, x1 prime u1 plus so on till xn prime un. Okay. Now, this and this gives you a way of equating these two guys and getting an equation. So, this gives you a set of equations, and this is what will let you go from x1 prime to e1 en. What do? I take u1 and substitute this guy. Okay. I take u2 and substitute the corresponding. So, until I take un and substitute the corresponding, and then group all the e1s together, and then I will get an expression for x1 in terms of these x1 prime, right. So, both of these have to agree. So, x1 becomes u11 times x1 prime plus so on till un to xn prime. So, this is the same as this equation. Do you see that? x1 to xn, which are the coordinates of u in canonical basis, have to be the same as x1 prime times the coordinate of u1 in the canonical basis. What is the coordinates of u1 in the canonical basis? u11 to un1, u11 to un1 plus so on till xn prime into coordinates of un in the canonical basis, and that is u1n all the way down to unn. Is that okay? So, this way I can go from x1 prime to xn prime to x1 to xn. Okay. But notice what this matrix is. This is an invertible matrix. Okay. This is a matrix of some invertible operator. Why? Because the columns are linearly independent. Do you see that? Because they are all bases, no? They are basis vectors, so columns are linearly independent. So, I can invert this matrix. How do I go from x1 to xn to x1 prime to xn prime? How do you do the reverse? I can just do T inverse. Okay. So, take this to this side, which means this matrix inverse multiplied by x1 to xn will give you x1 prime to xn prime. Okay. So, this kind of an idea you should be very clear on. When I change basis, go from canonical to this guy, right, all I have to do is take this basis vector multiplied with the inverse, I will go to x1 prime to xn prime. When I want to go from this basis to canonical, I just multiply the new basis, this x1 prime coordinate vectors with the basis itself. I get the canonical basis. Okay, very easy at some level, but it's good to keep a good understanding of how coordinates change when you change the basis for a particular vector. Okay, I hope you see this. Okay, so now comes the slightly more complicated case of a matrix of an operator. Now, here is a description. I have a linear operator T, it takes me from Fn to Fn. I have my famous this egg-shaped pictures for Fn, right? And then here I have a basis u1 to un. I am showing here as u1 to un, the same basis is here on the output side. It takes a u to v, right? So, let us say, okay, what does that mean? Now, to find a matrix for this operator T, I need to find out T of u1, T of u2, T of un, right? And this T of u1 to T of un, I have to express once again in the basis u1 to un to get the coordinates, right? So, that is how I make my matrix. So, let us say the coordinates of T of u1 are a11 to an1. the coordinates of t of un are an1 to an. Okay, likewise, t of ui is a 1i to ani. Okay, so those are the coefficients or coordinates of t of ui, right? So that's how I write it down. Now from there I know my matrix is a11 to an1, right? The coordinates of t of u1, then I have coordinates of t of u2, so on till coordinates of t of un. Okay, column wise if I write it down, that will give me my matrix M of t with respect to this basis u1 to un. Is that okay? So if I have a general u which is x1 u1 to xn u1, the coordinates of u are x1 to xn in the same basis, then the coordinates of v, if they are y1 to yn in the same basis, then I know the coordinates of v equals t of u is given by this matrix multiplication. That is how I define matrix multiplication, right? So this is what it is. So you take this, you multiply x1 by the first column, x2 by the second column, so on till xn by the last column, add it up, you will get y1 to yn. So we know how to do this. Okay. So now comes a slightly more complicated thing of changing the basis for a matrix. Okay. So you have an operator t, and then let's say somebody gives you a matrix M of t for it, and the basis is canonical. So usually while this t is an abstract operator, we always think of it in the specific canonical basis, right? Somebody gives you a matrix to define the specify the operator, right? You have to specify the output in every basis, and for every basis vector, and the basis vector usually you take as canonical. So this M of t is taken as canonical. Okay. So if v is the output, u is the input, M of t times the input coordinates is the output coordinates. So we know this. Now what I want to do is I want to go to a new basis, some other basis u1 to un, where each vector is now given as a these coordinates are over the canonical basis again. Okay, so u1 is given a set of n coordinates, un is given a set of another n coordinates. Likewise, every vector is given as set of n coordinates over the canonical basis. So I have a new basis now u1 to un. Now in this new basis, the same operator t will have a different matrix form, some m tilde of t it will be, right? How do I find this? I take t of u1, express it over the same basis u1 to un, I will get to a first column, and then take t of u2, express it over the same basis u1 to un, I get the second column, so on. But it turns out this m tilde of t and m of t are related in a very interesting way through matrix algebra, matrix product and inverse and all that. This m tilde of t and m of t are related, and they involve these coordinates of the basis vectors. Okay, how do you do that? That is what I am going to show you next. First is, we have my output v, y1 to yn as the original coordinates, let us say in the canonical basis, and then this v, same v, will have coordinates y1 prime to yn prime in the new basis, and we know our relationship between yn prime to y1 prime and y1 to yn, right? So, it is basically the inverse here times the original coordinates gives me my new coordinates in the new basis. Or if I want to reverse it, I can also multiply it by the this matrix on this side, I will get the other way around. So, this is just one equation. Likewise, also on the input side, right? Supposing u now has coordinates x1 prime to xn prime in the new basis, I know what the connection between x1 to xn and x1 prime to xn prime are. So, this is known, these conditions are known. You simply substitute here and do some algebra, you are going to get this guy, right? y1 prime to yn prime has to be m tilde of t times x1 prime to xn prime. Okay. Now, you use these relations, substitute them here and do an equality, you will get this magic formula, this m tilde of t is the same as this. So, let me show you how this is done. Okay, this is quite easy. So, you see m of t times x1 to xn became y1 to y1. And then what do I know? x1 to xn is this basis matrix, right? Basis matrix times x1 prime to xn prime. Same thing is true to y1 to yn, y1 to yn, and this is an invertible matrix, same matrix times y1 prime to yn prime. Now, if y1 and x1 are related through m of t like this, there should be a relationship between x1 prime and x1 prime, right? So, instead of x1 to xn, I am going to put this guy. Okay, what will I get here? So, m of t times this basis matrix, I am just writing it in painful generality here. So, hopefully you see this, times x1 prime to xn prime has to be equal to the same matrix you write down, sorry, 1n, un1 to unn times y1 prime yn prime, right. Now I know this matrix is invertible, so how do I take it to this side? I multiply both sides with inverse of this matrix. So be careful about commutativity and all that. So you will get y1 prime to yn prime, multiply both sides on the left with the inverse of this matrix. I am going to get u11, u1n, un1, unn inverse times m of t times the same matrix, the basis matrix. You can call it the basis matrix if you like. Okay, matrix whose columns are the original basis vector. So this guy times times x1 prime to xn prime. Hopefully you see that. Okay, so this guy is nothing but m tilde of t, and that's all that I've written there. Okay, see m tilde of t. Just substituting these guys back in here, you will get m tilde of t is the inverse of this basis matrix, m of t basis matrix. So this is a nice thing to sort of keep in mind how this is derived. Okay, so if you are given the matrix of an operator on the canonical basis and any other basis, there is a direct formula that converts to the basis, the new matrix in the new basis, which is m tilde of t, which is just inverse of this matrix times m of t times that basis matrix itself. Okay, you can also do the reverse. Okay, the same in reverse. I am not going to go into great detail here. The final formula alone is very easy, right? You can just take the original formula, multiply by the inverse on both sides to get to this form, or you can start from here and write it down. You will get the same answer. So m of t is m tilde of t, but now the basis matrix comes on the left, the inverse matrix comes on the right. Okay, so you can write it down and do the algebra of it, multiply on the right by something, left by something to shift both these matrices to the other side. Okay, so you'll get that, and that is where you get this guy, right. So hopefully you see what I meant by that, right. So you have this relationship, right, m tilde of t is this into this into this. Multiply on the left by the basis matrix, so this will disappear, right. When you multiply by the basis on the left, the inverse on the left will disappear, you will get the basis matrix on the left. And multiply by the inverse of the basis matrix on the right, this guy will disappear and you will get the inverse on the right hand side. So that's what is this relationship, right. So m of t is the basis matrix m tilde of t times the basis matrix inverse. Okay, so this way we can go between matrices according to different bases just by a simple formula involving basic matrix multiplication and inverse. Okay, so here is an example. Let's try that. Okay, for a matrix A, you find A is given as this. You find an eigenvector basis. Once you find an eigenvector basis, find a matrix S such that S inverse AS is diagonal. Okay, so let's try and do this problem. 1, 1, 1 on the diagonals, 3 on that side, and that's it. Okay, matrix A is 1, 1, 1 on the diagonal, 0, 0, 0 on these sides, and 3. Okay, so I'm going to do determinant A minus lambda I. So now, once I'm used to doing all these things, I know A minus lambda I is going to be a lambda subtraction on the diagonal. Then I will do my my 1 minus lambda cube, right? And then in my determinant, the second term goes away. Then I have a plus 3 times. Notice this 1 minus lambda here. Don't forget the 1 minus lambda. 0 minus 3 into 1 minus lambda. So you get minus 3 times 1 minus lambda equals 0, right? So 1 minus lambda will come out. Okay, don't cancel it off. Keep the 1 minus lambda. And then I'll have 1 minus lambda squared. So 1 minus 2 lambda plus lambda squared. Right, 1 minus lambda went out, and then I got a minus 9 equals 0. So the polynomial that you have is 1 minus lambda, lambda squared minus 2 lambda minus 8 equals 0. So you have lambda equals 1. Then here you have 2 plus or minus square root of 4 plus 32. Okay, so you can write it as 4 and 2 by 2, which is basically 6, right? So plus or minus 6. So you've got 4 and minus 2. Okay, so I hope I'm right. Okay, so lambda is 1, 4 and minus 2. Those are my 3 eigenvalues. So now I need eigenvectors, right? So A minus A minus I is basically 0 0, whole bunch of 0 0 0. So, immediately you see it is diagonalizable, there are distinct eigenvectors. So, you do not need to bother about it. So, if you do this, the basis is this eigenvector is 0 1 0, it's sort of obvious. So, 0 1 0, you can see 0 1 0 multiplies gives you 0 1 0. So, it is a eigenvector, there is no problem. So, V1 is that. So, what if you do A plus 2i, I will do minus 2i, it is go in increasing order of magnitude, minus plus 2i. So, it is going to be 3 0 3 0 3 0, right, plus 2i 3 0 3. Okay. So, this has got okay. So, hopefully you can see. So finding null space vector, see these two are equal, right. So, finding null space vector, you can do a lot of things, but you can see to do all this. So, you see clearly 1 0 minus 1 will be a null space vector here, right. So, this will give you 0, this does not matter, these two are equal. So, it just becomes 0. So, these are just quick shortcuts that will simplify your work sometimes. Okay, A minus 4i is going to be minus 4i. So, it is all minus 3 minus 3 minus 3. It is easy because on the diagonal nothing else changes, 3 3. What will you do here? Can you quickly identify? Maybe you can pause and identify before I write down the answer. I am going to write down the answer now. If you want, you can pause it and then think of yourself and see if you get it right. So, you see the first and third column, they are minus of each other. So, if I just do 1 0 1, I will get 0. So, my 3 eigenvectors are 0 1 0 with eigenvalue 1, 1 0 minus 1 with eigenvalue minus 2. So, 1 0 1 with eigenvalue 4. So, in the basis, what is my basis? 0 1 0, 1 0 minus 1 and 1 0 1. So, you do not even have to check this is a basis, right. They ended up being eigenvectors of distinct eigenvalues. So, they will be linearly independent, all of that is guaranteed. In this basis, my matrix becomes, matrix of the operator becomes 1 minus 2 4. Okay. So, let us check that. So, what do we know? This is my m tilde of t, right, in this basis, and this is my m of t, right, in canonical basis. So, what do I know my brilliant formula to be? So, my m tilde of t, which is 1 0 0 0 minus 2 0 0 0 4, which is a diagonal matrix, right. Remember, this is going to be equal to m of t, which was 1 0 1 1 1 3 here, right, 3 times what? So, you can go back and check and confirm, right. For m of t, you got the inverse on the left and the basis matrix on the right. So, you got this inverse. What is the basis matrix? The first vector comes here, second comes here, 1 0 1 comes here, the inverse times 0 1 0 1 0 minus 1 1 0 1. How do you check this? You might think you need to find the inverse of this. There is no need. You can multiply both sides by this. All you have to check is that these two are equivalent to 0 1 1 1 0 0 0 minus 1 1, multiplying 1 0 0 0 minus 2 0 0 0 4, and this has to be the same as 1 0 3 0 1 0 3 0 1 0 1 1 1 0 0 0 minus 1 1. Okay, you can check these two products. They have to be the same. Multiplying on the right by a diagonal matrix is very easy. This will just scale columns, 0 1 0 minus 2 0 2 4 0 4. Okay, so this is a slightly more important, more difficult, but you can just do dot products, right. So, this dot product with this will give me the first value, which is 0. This dot product with this will give me minus 2. This dot product will give me 4. It should be the same as this. I am just checking. I will get 1 here, and then you will get 0 0. Okay, and the last one will give you 0, and then 2, and then 4. There you go. Correct. We got it checked, right. So, notice that this diagonal matrix, okay, right, this is a diagonal matrix and this was written as S inverse AS, right. This is S inverse AS, the diagonal matrix. Okay, so this matrix is diagonalizable and I found my matrix. Okay, so it's very simple. I hope this example also helped you to clearly understand. Sometimes when you do it in notation, it's a bit confusing. When you see an example like this, it's very, very clear. You also try other examples, and it will see that these kind of things are easy to find out usually. I think if you have a numerical tool with you for finding roots of equations or even finding eigenvalues, eigenvectors, many computer tools will give you, can easily access that and get this done. Thank you very much.